Hello, everyone. This is Yinzhan. In this talk, I will talk to you about my joint work with Timothy Chen and Virginia Vassilevska Williams, titled Algorithms, Reductions, and Equivalences for Small Weight Variants of OPS Shortest Passes. Let me first give you the definitions of the problems we study and the motivations for our work. So as a key problem in our study, the unweighted APSP problem is a very important problem in the study of graph algorithms. In this problem, we are given an unweighted directed graph with n vertices, and we need to compute the distance between every pair of vertices. The current best algorithm by Zwick runs in O n to the 2.529 time. The runtime becomes O tilde n to the 2.5 if omega, which is a square matrix multiplication exponent, is 2. Zwick's algorithm can also be used for other variants of OPS shortest path in the same running time. For instance, APSP in a graph with integer edge weights between -c to c for some c equals 0.1 can be computed in the same running time. Also, OPS longest passes in an unweighted directed acyclic graph can also be computed using Zwick's algorithm. So it is very natural to ask whether these similar problems with same running times are actually equivalent or not. That means if we improve one problem, does that necessarily imply the improvements for another problem? Note that this is non-trivial because, for instance, if you want to relate unweighted APSP and unweighted OPS longest passes in a deck, then the most natural thing to do is to negate all the edge weights. However, then you get instances with -1 edge weights, and it's unclear how to convert these instances back to unweighted instances. So as the first fine-grained result, we show that in fact, these 3 problems we mentioned are equivalent. And we also show some other problems are in this equivalence class as well. In our second fine-grained result, we actually show some hardness result based on assuming unweighted APSP cannot be improved. So if any of the following problems has a faster than n to the 2.5 time algorithm, then so does unweighted APSP. I won't go into the details of the definitions of these problems, but if you are interested, you can read our paper. Complement to our fine-grained results, we also give algorithmic improvements for many variants of unweighted APSP. The first of them is the additive APSP approximation problem. So in this problem, we need to approximate OPS shortest path distances, but the amount of error allowed depends on the actual distance. So if the actual distance is DUV, we allow an additive error of DUV to the power of P. The running time of this problem will depend on P, and it is always between O n to the omega and O n to the 0.529. For the current bounds of rectangular matrix multiplication, we actually improve the previous best algorithm by Rodity and Shapira for all values of P strictly between 0 and 1. So for instance, when P is 0.5, we improve the running time from roughly n to the 2.447 time to n to omega time. Our second algorithmic result is about the OPS lightest shortest path problem. So in this problem, since a pair of vertices can have many shortest passes, we are interested in finding the shortest path with the smallest number of edges. The previous best algorithm by Zwick runs in O n to the 2.724 time, and it was improved by Chen to O n to the 2.687 time, but only if the weights are positive. Note that in the original problem, the edge weights can be 0 as well. So Chen's algorithm does not handle that case. We show an O n to the 2.66 time algorithm for this problem. This does not only improve Chen's algorithm, but also allows 0 edge weights. when the graph is undirected, we can further improve the running time to O(n) to the 2.58 time. We also have other algorithmic results. One line of them is the many versions of APSP counting. So in particular, we can count the number of shortest passes exactly for every pair of vertices in a directed unweighted graph in roughly n³ time. And we also studied many other variants of APSP counting as well. Notably, our techniques also lead to a simpler algorithm for small weight undirected APSP, whose running time is roughly n to the omega by Shoshan and Zwick. So among all the algorithmic results, I will only have time to talk about the all pairs APSP approximation algorithm. If you are interested in other algorithms, please read our paper. Let me first define some notations. Omega, as we already used, it denotes a matrix multiplication exponent. Omega ABC denotes an exponent for multiplying an n to the A by n to the B matrix with an n to the B by n to the C matrix. And the rho is an important constant in this talk, and it is defined such that omega 1 rho 1 equals 1 plus 2 rho. Currently, we know that rho is between 0.5 and 0.529, and you may already notice that 0.529 is the running time for Zwick's algorithm. Mean plus product between two matrices A and B is a matrix C such that Cij equals the minimal over OK of the value Aik plus Bkj. And we use mean plus N1, N2, N3 with value W to denote a special instance of mean plus product. So specifically in this instance, we need to compute the mean plus product between an N1 by N2 matrix and an N2 by N3 matrix, where the entries of both matrices are either small integers bounded by W or infinity. And we use M, N1, N2, N3 with weight W to denote the running time of the above mentioned mean plus product instance. So if we use a brute force algorithm, then the running time can be bounded by N1 times N2 times N3. There's an algorithm shown by Alon, Galileo, and Margalit that solves the small weight mean plus product problem in O tilde W times omega ABC time. So now let me first tell you the proof of our fine-grained equivalence. But before that, I'll give a review of Zwick's algorithm. So Zwick's algorithm solves the unweighted APSP problem in O tilde n to the 2 plus rho time. And the high-level idea is to compute small distance first, and then use them to compute large distances. Suppose we already computed pairwise distances at most L. So in other words, we already have a matrix D prime such that D prime UV equals DUV whenever DUV, which is the actual distance, is upper bounded by L, and D prime UV is infinity otherwise. And using the matrix D prime, we are aim to compute the distances that are at most 1.5 L. So key idea in Zwick's algorithm is to use the notion of the bridging set. So consider the shortest path from U to V, which has length between L and 1.5 L. We use middle third to denote all the vertices that can be reached from U in L steps and that can reach V in L steps. Now, because of the upper bound 1.5 L, the middle third has at least 0.5 L vertices. Therefore, if we sample a set S of n over L times log n vertices randomly, then with high probability, one vertex from the set S lies on the middle third. And notice that since the distance from U to S and the distance from S to V are bounded by L, D prime US and D prime SV are already correct. So That means d prime us plus d prime sv equals d prime duv. Therefore, for every pair of uv, we just need to compute the minimum value over OS of d prime us plus d prime sv. And this is exactly a mean plus product instance. So here we are using d prime vs to denote a submatrix of d prime, where the first coordinate can be any vertex, and the second coordinate must be a vertex in the sampled set. So the dimension of this mean plus product is n by n over L by n, and all the weights are either infinity or bounded by L. So it's an instance of mean plus n over L n with weight L. And therefore, the running time of Zwick's algorithm is roughly the following quantity. Now, it remains to bound this quantity. When L is large, say L is at least n to the 1 minus row, then we use the brute force algorithm for mean plus product, and that can bound the running time to n to the 2 plus row. When L is small, say capital L equals n to the little l, then we use Along et al.'s algorithm for mean plus product. Now, this case is slightly more complicated than the previous case, but by noticing that omega 1 minus L1 can be represented by some constant plus omega 1 rho 1, and we can plug that into the original running time, we also get an n to the 2 plus rho running time. But I will skip most of the masses here. Yeah, so Zwick's algorithm runs in the claimed running time. So with Zwick's algorithm, with ideas from Zwick's algorithm, we can prove our mean equivalence that shows unweighted APSP is sub n to the 2 plus row time equivalent to these instances of mean plus product. So if one of them has a faster than n to the 2 plus row time algorithm, then so does the other. Now, suppose mean plus product between n by n to the row matrix and n to the row by n matrix with weights bounded by n to the 1 minus row has an O n to the 2 plus row minus epsilon time algorithm. And we aim to show a truly sub n to the 2 plus row time algorithm for unweighted APSP. Our reduction will be a modification of Zwick's algorithm, and we can use the same running time from Zwick's algorithm, that is max L of m n over L n with weight L. As we can imagine, when L is much larger than the boundary n to the 1 minus row, or when L is much smaller than the boundary, it's intuitive that the running time of Zwick's algorithm is strictly better than n to the 2 plus row. So when L is greater than n to the 1 minus row plus delta for some small positive delta, we use the brute force algorithm for mean plus product, and we get sub to n to the 2 plus row time. And the case when L is less than or equal to n to the 1 minus row minus delta is slightly more complicated, but we can also bound it as truly sub n to the 2 plus row time. Now, the remaining case is when L is very close to n to the 1 minus row. Say L is between n to the 1 minus row 1 minus delta and n to the 1 minus row plus delta. And in this case, mean plus n over L, n with weight L is actually a special case of mean plus capital N to the power of rho, capital N with weight capital N to the power of 1 minus rho for some capital N equals n to the 1 plus 10 delta. This is because all the corresponding coordinates and weights of the second instance is smaller than that of the first instance, as you can verify via these equations. So therefore, since the first instance is a special case of the second instance, we can just bound the running time of the second instance, which by the assumption there is a truly capital N to the truly sub capital N to the power of 2+ row time algorithm for that. And indeed, if delta is small enough, then this running time is also truly sub n to the 2+ row time in terms of little n. Therefore, this case is also truly sub n to 2+ row time. And this concludes the proof of the first direction. Now for the second direction, suppose unweighted APSP has an O into 2+ row minus epsilon time algorithm. And we want to use that to get a faster algorithm for this mean plus product instances. Recall that we want to compute a matrix A star B, where the edges entry is the minimal value over OK of AIK plus BKJ. So given the mean plus product instance, we create the following graph. On the left, there are n vertices denoting indices I. On the right, there are n vertices denoting indices J. In the middle, there are n to the power of row passes, and each pass has roughly n to the 1th row vertices on it. Also, for each pass k, we use xk0 to denote the middle vertex on that pass. So from each I to each pass k, we add an edge from I to some vertex on this pass, and that vertex has a distance aik to the middle vertex. Also, for each k and each j, we add an edge from some vertex to j, and that vertex has distance bkj to the middle vertex. So now, if we think about the shortest path from I to j, it has n to the row choices, one choice for each k. And if the shortest path uses the case path, then the length of that shortest path is 1 plus aik plus bkj plus 1. Therefore, the distance from I to j is exactly 2 plus the edges entry of the mean plus product A star B. Therefore, given the shortest passes, it's very easy to get the mean plus product. And thus, if APSP, unweighted APSP can be computed faster, then so does mean plus product of this form. Now, we prove our mean equivalence, and we note that there are many other equivalents we can prove using similar ideas, and this results in all these problems in the rectangular that are equivalent to each other. Also, using the similar ideas, we can show some hardness results as well. Okay, so now I will talk about our algorithm for additive APSP approximation. Recall in the additive APSP approximation problem, we are given an unweighted directed graph and a constant p between 0 and 1. We need to compute for every pair of vertices u and v an estimate d prime uv, such that d prime uv is between duv and duv plus duv to the power of p, where duv is a real distance. The previous best algorithm by Rodity and Shapira runs in time the maximum value over OL of mean of these two quantities. And we improve the running time to the following quantity, where it's still a maximum over OL, but the inner quantity is smaller than their inner quantity. So in fact, if we compare our inner quantity with n cube over L term, then by the brute force algorithm of mean plus product, we know our quantity is always upper bounded by their quantity. Similarly, we can compare their second term. Notice that their second term is also a mean plus product, but their inner dimension is n over L to the power of 1 minus p, and our inner dimension is n over L. So our inner dimension is always not larger than their inner dimension. That means our algorithm is actually an improvement, at least for some values of p. And in fact, for the current value of rectangular matrix multiplication, our algorithm is a strict improvement. For all p, that's strictly between 0 and 1. Our algorithm uses uses the bridging set idea of Zwick's algorithm. So for each L that's the power of 1.5, we sample a random subset of vertices SL of size roughly n over L. Further, we can assume S1.5L is a subset of SL by adding all the smaller subsets to all the larger subsets, and this won't change the bound of our subsets. In the first step of our algorithm, we compute as many distances as possible exactly in O tilde n to the omega time. So specifically, we will compute the distance from U to V for every U that's in SL and for every V that's a vertex. And additionally, we only compute the distance for these pairs DUV that are bounded by L. Now we will do this iteratively for each L. And suppose we did this for L already. Now we move to 1.5 L. If DUV is at most L, then it's already computed since S1.5L is a subset of SL by assumption. If DUV is greater than L, then since SL is a random subset, by our previous argument, SL contains a vertex landing on the middle third on the shortest path from U to V. Therefore, it suffices to compute the mean plus product. And we can write the total cost in terms of the running time of mean plus products. And you can verify here that this running time is actually at most n to omega. Our second step will actually do the approximation. So for each L that is a power of 1.5, we will approximate DUV, where DUV is between L and 1.5L. By the hidden set argument, it suffices to compute the mean plus product DVSL star DSLV after we remove all entries that are larger than L. Since we need an additive OL to the power of P approximation, we can further round all entries to multiples of OL to the power of P. And we can, of course, further divide these entries by L to the power of P. Therefore, the cost is n over Ln with weight L to the power of 1 minus P, because the original weights are L, but we divided them by L to the power of P. And this gives the desired running time. In fact, in our paper, we show that the running time we obtained is actually optimal in a strong sense. So we get that additive APSP approximation with parameter P and N is requires this amount of running time. And this matches with the running time of our algorithm up to polylogarithmic factors. Okay, so that concludes this talk. So recall that in our paper, we establish sub n to the 2 plus 0 equivalences and harness among many variants of unweighted APSP. And we also design faster algorithms for some of these variants and even show conditional optimality for some of our algorithms. Thank you.